Question 18. A manufacturer of spring tests properties of a spring by measuring a load applied each time extension is increased. The graph shows load against extension, so force against extension. So here you've got the original graph, and then I've got my additions for the rest of the question. So let's start off. State Hooke's law. Hooke's law, force is directly proportional to the extension. You can write it like that as well, up to the limit of proportionality. There's your second mark. That's a straight section of the graph. So Hooke's law only applies for the straight section of the graph. Okay, point A is beyond that straight section, so we're not considering A in this scenario here. Use a graph to calculate the spring constant K. So the spring constant, or also known as the force constant, is the gradient of a force extension graph. So there's my triangle there. It's on the straight section of the graph. Anything that's curving off, I shouldn't use. So I'm using the straight section here. There's a straight section, and it is 30 in height and 0.026 in width. And the gradient of a force extension graph is the force constant, and y2 minus y1 over x2 minus x1. So I've used the two coordinate points here, that one point there and that one point there, and that's 30 and 0.026, and that gives us 1154, and the unit is Newton per meter, as we are doing newtons dividing by meters. Okay, so that 3 sig fig, that will be 1150 Newton meters. Okay, there's no need to add in additional conversions because this is the correct unit, meters and newtons, for our calculation. If this was centimeters, all our x values needed to be divided by 100, and if that was kilonewtons, we had to times it by 1,000. However, that's not the case. The next question, part C, use a graph to estimate the work done in extending the spring up to point B. So let's identify where point B is, up to point B, and the work done is the area under a force extension graph. Okay, so this is this entire area, and it's an estimation as there's a bit of a curve here. So what I've done is I split it into sections. I split this section into a triangle. I'm using that same triangle as before. So it's the area of this triangle, the area of this rectangle. I've labeled it section B. This section here, label that triangle section C. And then this little area here that's remaining, I've labeled that section D. And that is my estimation. So I'm going to work out the area of every single section. So section A is a triangle. So it's 0.026 in width, 30 in height, times by half, so half base times height, I get an area of 0.39 joules. And then the area of section B is a rectangle. Okay, so there you go. It's the base times height, and the base is from 0.045 minus 0.026, and that gives us 0.019, multiplied by the height of 30 gives us a energy of 0.57, and then the triangle here, a height times by the base times by a half gives us an area of 0.0855. Then what I've done is I've worked out how many little squares roughly fall in this section here, and I've worked out the area of one little square here, which is 1 as the height and 0.001 as the width. So that's 0.001 as the area. And I've counted approximately 31 small squares and times that by the area of each individual little square as 0.031. Added up all the individual areas, I get a total of 1.0765 joules to 3 sig figs 1.08 joules. So that's how much work is done in extending the spring up to point B. It's the area under the force extension graph. Okay, so part D, beyond point A, the spring undergoes plastic deformation. Explain the meaning of the term plastic deformation. Well, if a material is under tension and a load is on it and it's being extended and stretched, there will be a point that it will reach, and that is known as the elastic limit. And if it goes beyond the elastic limit, and extends beyond the elastic limit, it will not return back to its original length. And any region beyond the elastic limit is known as the plastic deformation. So material has permanently deformed and gone beyond this elastic limit. That is the plastic region. Once the load is removed, the material will no longer return back to its original length. So when the spring reaches an extension of 0.045 meters, the load is gradually reduced to zero, and the graph sketch how the extension of the spring will vary with load as the load is reduced to zero. So what we need to do here is we need to draw the unloading phase, and that blue line there is the unloading phase. So as I remove the weight, it will return back to some deformed position, not back to its original extension, because we have gone beyond, as point A indicates, is its elastic limit. So beyond, once the material went past point A, now it was permanently deformed. And if we unload, we will return back to some new original length for zero force. So it's permanently extended by a certain amount. Now, how do we draw this line? The easiest way to do this is draw a straight line running straight back to the x-axis and try to make it parallel or close to parallel to the straight line that was from the loading phase. Now, this is, of course, making an assumption that there's not been any real deformation in the material's molecular structure. So it will still behave with the same kind of stiffness or a spring constant as it did before. But there is equally an argument for that it could become steeper, stiffer, or less stiff. So sometimes you could draw a gradient that is less than this or more than this, but not too much. The easiest way for your syllabus is to just draw a straight line parallel to the straight section coming back. That's what will pick you up the 2 marks. Right, the next part, without further calculation, compare the total work done by the spring when the load is removed with the work done by the load in producing the extension of 0.045 meters. So where is 0.045 meters? There we go. So what they are trying to ask you is what's the difference between the work done in the loading phase compared to the work done in the unloading phase. So the work done in the loading phase is by the weights, and the work done in the unloading phase is by the actual material, so the spring. And the area underneath the graph is quite considerably noticed. So the area underneath this section is less than the area underneath this section, the loading phase. So the loading phase is this whole area here, and the unloading phase is just this area here. So the work done in the unloading phase is less than the work done compared to the loading phase, or the work done by the spring during unloading is less than the work done by the load during the loading phase. And that's what I've written here. So the area in the curve during the unloading is less than the area while loading. Therefore, the work done by the spring while unloading is less than the work done on the spring while loading. So, linking area to work done and comparing the two different areas.